All right, so problem one, we got this histogram that shows the response of 100 people that are asked, what was the price of the last meal you purchased? And so we have to figure out what could be the interquartile range of the prices based on this histogram. All right, so let's remember the interquartile range is from Q1 to Q3. It's the distance. It's a distance from Q1 to Q3. So the first quartile or Q1, remember it's 25 percentile, and the third quartile is a 75 percentile. So we have to figure out where the 25th or 26th person, where the 26th to the 75th person would be. Like, where would they lie? So we have 8, so we just count 8, 21. Starting here, we go from 22 to 33. So this is actually, let me go here. So 22, 22nd person to 33rd. And then we look to see where the 75th person would be. Let's just go backwards. 1, 3, 8, 11, 16, 24. So then it would be somewhere in here. So the 75th person would be in here. Now, well, in here, in this interval, let me just do that, starting from here. So in here, let's do that. So we figure out what the range, what the possible values that are contained in that interval are. So we go from $9 starting here to not 17 but less than 17. So we're gonna go from $9 to like less than 17. So like, again, we could basically say, let's just say 16.99. Now, that doesn't mean that every value from $9 to like right before 17 is contained. Maybe remember, this goes from 15 to less than 17. So maybe it just stops at 15. Maybe all these 8 people where, I don't know, what are they paying for? Oh yeah, so maybe all these 8 people paid $15 for their meal. Doesn't mean that any of them had to even pay 16 or 17. So what the ones that would be possible would be, it can't be 10, it can't be, it has to be no more than 7, but it has to at least be, like 6 or 5. So the closest one will be D. That's the only answer that will be reasonable. But again, in other words, we don't know for sure if that's the exact value. That's the only one that we can say is possible. So make sure you understand that. $5 is only possible interquartile range. Or 2, suppose a certain scale is not calibrated correctly. As a result, the mass of any object is displayed as 0.75 kilogram less than its actual mass. What is the correlation between actual mass of a set of objects and the respective masses of the same objects displayed by a scale? Okay, so let's just do like a hypothetical. Let's say X's are the actual mass and Y's are the displayed masses. So let's say if something was like 1 kilogram, that would be represented as 0.25 kilograms. If it was 2, it would be like 1.25. If it was, it doesn't have to go in order. Maybe if it was 10, that'll be 9.25, 20, 19.25, and so forth. It's always 0.75 kilograms less than X. Now, so if you're trying to figure out the correlation between the actual masses, X, versus the respective masses that are displayed, so Y, the relationship between X and Y would actually be a perfect relationship because you could perfectly predict the Y values if you know the X values. The correlation would be 1. Again, that's because we know the correlation precisely. We know exactly we know what the exact relationship would be. Okay, number 3. And maybe if you need a review, remember this is dealing with the correlation coefficient R, going from 1 to -1. So there, that's usually covered in my course. It's chapter 3, but the chapter dealing with the relationships and correlation. All right, a veterinarian collected data on the weights of 1,000 cats and dogs treated at a veterinarian clinic. Whoa. The weight of each animal was classified as either healthy, underweight, or overweight. The data are summarized in a table. Based on the data in the table, which of the following is the most appropriate type of graphs visually show whether a relationship exists between the type of animal and the weight classification? Okay, so we have the types of animals, cat, dog, and whether it's healthy, underweight, or total, or overweight. So this would make sense to have essentially bar charts that are like grouped together for like cats and then dogs. So it's maybe something like this. You would have cats, and you would have maybe one for healthy, the one that displays underweight, and the one that maybe displays overweight. I'm not saying these are actual heights, but this is just a hypothetical example. And same thing for dog. Have a bar for healthy, another bar for underweight, and another bar for overweight. So this would be an example of like a segmented bar chart. We're basically using bar charts that like combined, sub-combined. So D. Now, the rest just wouldn't even make sense to do. I mean, if you want, like, why can't it be any of the other ones? It's just not even possible mathematically, like statistically or mathematically. It wouldn't even make any logical sense if you would try it. Okay. Suppose a certain. Oops, did I want to double turn it on? 4. A program exists to encourage more middle school students to major in math and science when they go on to college. Oh, right. The organizers of the program want to estimate the portion of students who, after completing the program, go on to major in math or science in college. The organizer will select a random sample of students from a list of all students who completed the program. Which of the following sampling methods describes a stratified random sample? So let's remember what stratified random samples are. They're basically samples that are subdivided into groups that would make sense for like having a possible effect on the results. So for example, like if you're like trying to figure out like let me think. Trying to figure out the a student's performance and how you're trying to determine if a student's what a student's performance in AP Calc would be. You probably want to stratify the data according to maybe GPA or maybe grade, because maybe the higher GPAs, because the GPA probably has a relationship in helping you predict how well a student would do in like a AP class. So maybe you want to see how the students with 4.0s and above, or 3.0s to 4 and 2.0s to 3, because then that will allow you to see if GPA is actually a significant factor on your performance in the AP math class. So what would make sense here, that you would probably want to subdivide, not select all around it. What would you subdivide? So D, because you're going to basically break the sample into female students and then male students. So we break it according to gender. So that would be like an example of a stratified sample. So again, a subgroup of the sample. And again, it would be like a variable that you think may have an effect on the result. And then that would just depend on the problem. All right, 5. The normal curve shown represents the sampling distribution of the sample mean for sample size n25 selected at random from population with standard deviation sigma sub x, which is the best estimate of the standard deviation of the population sigma sub x. Okay, so I mean, I actually have this memorized. You know, the sigma or the sample standard deviation is equal to the population standard deviation divided by the square root of the sample size. But if you don't have it memorized, no worries. That's why you got your formula sheet. You're allowed to use throughout the whole test. Make sure you know how to refer to it. So you could just, this will be the formula here. Well, no, actually, it's not. It will not be the formula. Yeah, over here. Or that actually is. Or, well, technically, well, not technically, but same sort of thing. Sample mean. So standard deviation of the statistic for sample mean. So this would be your S sub x. So standard deviation of a sample would be the population standard deviation divided by the square root of the sample size. So we're trying to solve for this. So since the sample size is 25, S sub x would be, you know, sigma sub x divided by 5. The square root of 25 is 5. Now, what is the sample standard deviation? Well, we're told that this is normal. This is normal with a mean of 150. And if this is normal, that means that it would have to follow the 68, 95, 99.7 rule. And that would also be based on the concavity or the inflection points. So one standard deviation away would be probably right around here, not 165, 135. Two standard deviations will be 180, 3 would be 195. So the distance from 150 to 165 would be 15. Or minus 15 if you want to get to 135. So the sample standard deviation would be 15. So 15 would be sigma sub x over 5. Multiply both sides by 5. 75 would be the population standard deviation. Make sure you know your algebra. So the answer would be E. At 6, 2 random samples A and B were selected at random. Were selected from, no, well, not at random. Well, yeah, were selected from the same population to estimate the population mean. For each sample, the mean standard deviation and the margin of error for 95% confidence interval for the population mean are shown in the table. Which of the following can explain why the margin of error of sample A is greater than the margin of error for sample B? It is greater. Let's kind of just let's remember the the whole concept of the margin of error. It's pretty much what it sounds like. What you would expect to miss the true value, true population parameter by, like how often you think your estimates would be by average. So like when we make confidence intervals, we're not gonna know precisely if it's gonna contain the population parameter. So we have this margin of error that kind of tells you, how this will let you know how wide the confidence interval will be. In this case, you will have your sample mean, and distance from one endpoint to the other would be your margin. Plus to the right and negative to the left. Anyways, you obviously want smaller margin errors because you're gonna get more precise estimates. Now, just think about it. The more data you have, the more precise your estimates can be, just because you have more information. So a possible reason could simply be that sample size A is smaller than sample size B. So when you have less information, less data, your estimates are going to be less precise. So your confidence interval will be bigger, simply because you have smaller sample size. All right, 7. Naisha's financial literacy project involves comparing the annual sales of companies in Canada and companies in the United States that produce software. Using the ratio of 1 Canadian dollar to 0.75 United States dollar, we converted all annual sales from the Canadian companies into US dollars. Which of the following will the value of the statistic for the annual sales in Canadian dollars be equal to the value of the corresponding statistic in US dollars? Okay, so 1 Canadian dollar, let's just say 1 C equals 0.75 United States 0.75 U. Now, if you know $1 Canadian is equal to 0.75 United States dollar, it wouldn't make sense for like any of the true values of the distribution of Canadian dollars to be equal to any of the true values in the United States dollar. So it wouldn't be median. The medians would not be the same because again they're different. Like $1 Canadian is worth 0.75 US dollars. So if the mean of the Canadian dollars was like 1, then the mean of the United States dollars would be 0.75 times 1 or 0.75. So that would apply to standard deviation measures of spread as well, measures of center spread, but the standardized score that basically takes into account the relative values. So it tells you only, remember, standardized values tell you within a distribution like how like where it lies. So for example, we need a little review. The standard normal curve has a mean of 0, standard deviation of 1. 50% to the right, 50% to the left. If you're basically, converting, calculating maybe your height, where your height would lie, and then the distribution of heights we know is normal. Like the mean height would be in the middle. The mean height of the last time I checked of males in the US was 5'9" or 69 inches. So even though these values are different, the standardized scores are the same. They both have a standardized score of 0, meaning they're both equal to the mean of their distributions. So it would be C. It also works in sports if you're wondering, like the number one score, in each league, maybe like or the fastest person in each league, if you're doing track, maybe. They could have different times, but relative within their own group, they're going to line and say they're going to be equal to the same place. They're all in first place relative to their groups or leagues. All right, 8. The manager of the restaurant lacks the types of dinners that customers order from the menu to ensure that the correct amount of food is ordered from supplier each week. Data from customer orders last year suggests the following weekly distribution. Here are type of dinners and their proportions. The manager believes that there might be a change in distribution from last year to this year. They took a random sample of 200 orders, so let's write n as 200. We can take a note of that. Random sample, 200 orders were taken from customers ordered placed last week. And this table shows that data. Assume each order is independent. For which type of dinner is the value of its contribution to the appropriate test statistic the greatest? Okay, so remember, we're trying to figure out if there was a true change, or more statistically speaking, was there a significant change in each of these values, but since they're measured in different stats, let's convert them to both the same. This proportion 0.18, frequency 32 out of 200. So let's make these all proportions, and then let's see how they all change. So 18%, 32 out of 200 would be 16%, or 0.16. 41%, 0.41, 86 out of 200 would be 0.43, 0.15, 34 out of 200 would be 0.17, 0.2 to 30, 30 out of 200 would be 0.15, and from 0.06 to 18 out of 200 or 0.09. Okay, so we can see that they did change in their proportions. But here's the thing. You don't just look at the raw amount, meaning that we don't look at like we were not like even though it's a pork changed by 0.05, fish changed by 0.02, chicken changed by 0.02 as well. This beef changed by minus 0.02, and vegetarian changed by plus 0.03. The answer wouldn't still be pork, even though pork has the greatest value change by 0.05, even though that's the biggest. That's not what we're technically looking for. We want to basically compare its relative change to itself, meaning that from 0.06 to change of 0.09, that's a relative change of 50%. It increased by 50% of what it used to be, which is great, which is a massive amount. Because and that's because 0.06 times 1.5 will be 9%. To change 6 to 9, you would multiply 6 by 1.5, meaning that you basically increase the value of 6 by 50% of its amount. For pork, you increase by 5 or 5 out of 20. This only basically had a relative change of 25%. Oops, 25%. And these ones would you can do the calculation, but you can already tell that it's not going to be that. So the answer would actually be already vegetarian. And this is actually important for you to know, and I think most people should know this because a lot of people always make this mistake where, like, if you were saying like, oh, I want to have an improvement of 10%. Let's say you play basketball and you score 20 points a game, and you say you want to improve by but if you want to improve by 10%, 10% of 20 would be 2, so you want to improve by 2 points. However, when people like take a test, like you're taking a test, and let's say you normally get 80 out of 100, and you say you want to improve by 10%, most people would think, oh, I want to go from 80% to 90%. 80% to 90%. Now that is a raw total of 10% increase, but relative speaking, if we're talking about relative percent, 10% of 80% is 8. So increasing by 10%, relatively speaking, it would be going to 88%. So there's a difference. So make sure you understand that, because it's going to be a big deal when you go into more stats classes and a lot of science classes.